welcome back, folks, and the topic of today's video is going to be an introduction to thermochemistry, sometimes also known as thermodynamics. Now, what thermochemistry is a study of the energy change or changes that accompany some chemical change. Now, a chemical change, as we know, is really nothing more than a chemical reaction. So anytime a chemical reaction occurs, we know that there is a change in energy associated with that, and it's that change in energy that we want to measure. So for example, some reactions, when they happen, might give off heat. Other reactions, when they occur, might actually take in heat. Okay, so both of those things actually refer to some sort of a change in energy associated with that reaction. Now, in order to understand this a little bit better, we have to set out some conventions here that we need to use so that we can tell something about the direction of transfer of energy, say in the form of heat. All right? So, we can start with the system. So the system is always going to be our point of focus. Now, if we're talking about a chemical reaction, then the system is that chemical reaction. That's where we want to focus, so we can see what the change in energy looks like from the point of view of that system. Now, we also have to think about the surroundings. Now, the surroundings are everything else that are in contact with the system. Now, when we put the system and the surroundings together, what we have is a quantity called the universe. Okay, so the universe is the system plus the surroundings. Now, let's take a look at a simple example of this to get an idea of what we're talking about. So let's say that I've got a reaction running in a beaker. All right, so all the reaction components are here inside the beaker. So, in a situation like this, a reaction is occurring, and there's going to be an energy change associated with that reaction. All right, so where we want to focus is on the system, and the reaction inside the beaker is actually going to be that system. But now we want to see, for example, what direction the energy change might take. So if we think about this in terms of the flow of heat, and that's one way of thinking about energy, if the reaction, for example, is giving off heat, where does that heat go? All right? So the heat has to be transferred from the reaction to the system. Now, from the reaction to the surroundings. Now, what are the surroundings? Well, that's everything in contact with the reaction, which is our system. So, for example, the surroundings could be the beaker that contains the reaction. The system, or rather the surroundings, could be the air surrounding the beaker and the contents of it. The system also could be the tabletop. So, for example, if the reaction is giving off heat, that heat could be absorbed by the beaker. It could be absorbed by the air around the beaker and around the reaction. And some of that heat could also be absorbed by the tabletop. All right? So that's why we need a system in the surroundings, so we can see the direction of flow of energy. So the energy has to come from somewhere, and it's got to go somewhere. All right? So I mentioned to you that one specific type of energy that's of interest to us as chemists is heat. Now, the other type of energy that's of interest to us is actually work. Now, normally when we talk about energy associated with work, we're talking about, for example, expansion of a gas against its environment. Okay, so as a gas expands, the gas does work. All right, so let's think about this in terms of the simple definitions of each. Heat is considered to be the energy transferred due to a difference in temperature. So you guys know, for example, if I were to take a hot object and toss it into a beaker of water, what's going to happen? We know that the object will transfer its heat to the water and the beaker until they come to thermal equilibrium. In other words, the temperature associated with the water will be the same as the temperature associated with the object. That's what I mean by thermal equilibrium. So heat, by definition, is energy transfer due to a difference in temperature between two objects that come into contact with one another that ultimately need to reach thermal equilibrium. Now, the other type of energy that we can talk about is work. As I mentioned, work is often thought about in terms of expansion of a gas against its environment. All right? So that could be, for example, a gas expanding to move a piston. That's physical work. Now, what is work then? Our physics definition of work is a force applied to an object to push it across a certain distance. So if I have an object down on the tabletop here, all right, and I do work on it, what I'm doing is I'm pushing it from one point to another. Okay, I'm applying a force to that object across a particular distance. All right, that's work. Now, in both cases, whether we're dealing with heat or work, the energy is going to be measured in terms of a quantity called joules. So the joule is the basic SI unit of energy. Now a joule broken down into its common SI units is this. 1 joule is equal to a kilogram times a meter squared, all of that divided by a second squared. All right? And you can actually derive that from this relationship here for work. Force, remember, is in terms of newtons. Distance is in terms of meters. So you guys should be able to come back and recognize that work is a newton times a meter. If I break a newton down into its common SI units and put the meters in there as well, I'm going to get kilograms times meters squared per second squared. And remember, a newton is a kilogram meter per second squared. I think we talked about that back in the gas law chapter when we dealt with pressure. All right? So the next thing we want to talk about in just a moment is a breakdown of energy in terms of a broader view, which would be a comparison of kinetic energy versus potential energy. So we'll get to that in just a moment. So as I mentioned, we can talk about energy in a bit broader terms. And this is something you guys are already familiar with because we talked about it in the gas law chapter very recently. So for example, in that gas law chapter, when we talked about kinetic molecular theory, we talked about the kinetic energy associated with the particles of the gas in the ensemble. Now we know that kinetic energy is energy associated with movement or motion. All right, so if I have a moving body or a moving particle, that particle will have kinetic energy associated with it. Now we also know that there's an equation for kinetic energy. We know that kinetic energy of any moving object is equal to 1/2 the mass of the object times the velocity of the object. All right? So that's kinetic energy. Now the other type of energy is potential energy. Now that's one we've not talked so much about. Now potential energy is considered to be stored up energy or energy associated with something's position. All right, so if we talk about, for example, stored energy, what we're talking about there is, for example, the energy that we would find in a battery. All right, so we know that in a battery we can store up energy as potential energy, and then when we place that battery into a circuit, we can tap into that energy and then convert it to kinetic energy, for example, to do something like light up a light bulb or, for example, run a motor. All right, so that's an example of stored energy. But what about energy associated with position? Well, in this situation, we're talking about energy associated with an object's location. So for example, if I place my marker here on the table, we could say that the marker has potential energy associated with it by virtue of its position. The reason for that is because if I roll the marker off the table, it's going to fall to the floor, and when it hits the floor, it's going to do work on the floor, right? So that's a good example of energy associated with position. So a falling object is a good example of that. Now the important thing for us to remember when we deal with thermodynamics is that energy can be converted between kinetic energy and potential energy. Our battery that we already mentioned was a very good example of this. Okay? So we store up the energy as potential energy in a battery, and then as I mentioned, when we place that battery into something like a flashlight, or we place it into a cell phone or something like that, that potential energy then can be converted to useful kinetic energy. So for us, kinetic energy is the useful kind of energy to tap into. Now, we also know that we can then recharge the battery in our cell phone. Okay, so we plug our cell phone in. What are we doing? We're actually using electrical energy to then drive that reaction in reverse and then return the battery to that charged state. Okay, so in a sense, that's movement of kinetic energy back to potential energy through electrochemical reaction. Another good example of this would be an automobile engine. So if you think about how an automobile engine works, we burn gasoline. It's actually a mixture of gasoline and air, right? In a combustion reaction. So the gasoline has potential energy associated with it. That's energy stored up in the chemical bonds. Now, when we burn the gasoline in the presence of the oxygen, you guys know what we make. It's a combustion reaction involving a hydrocarbon, so we make gaseous carbon dioxide and gaseous water vapor. Now remember, there's a lot of heat generated in this reaction as well. That's why those products are in the vapor state. So what happens when we heat a vapor? Well, you guys know from your gas law chapter that when you heat a gas, that gas expands, okay? So as a result, through expansion of the gas, that gas can expand against a piston in the automobile engine, which can then, of course, be attached to a crankshaft, which ultimately turns your wheels. So that's a good example of conversion of potential energy over to kinetic energy, okay? So stored up energy in the form of chemical bonds in gasoline being converted to kinetic energy associated with the movement of the car. So we can see that we can convert from one kind of energy to another, kinetic potential or potential back to kinetic. All right, probably a good place to stop for now, and we'll see you guys next time.